Hi all, welcome to another session from Nairo Research. I'm Srijit here. So in this session, I'm focusing on the applications of NEB or nudged elastic band method, which is one of the computational technique used to find the minimum energy path or MEP between two known states of the system, like the reactant and product of a chemical reaction. So the highest energy point along this path is the transition state, which is crucial for determining the activation energy and reaction mechanism. And also NEB, speaking about NEB, it works by optimizing a series of intermediate images or replicas of the system that are connected by virtual springs. So the forces on each image are carefully controlled. For example, a spring force pulls along the band to keep the images equally spaced, while a force from the potential energy surface pushes the images perpendicular to the path, nudging the entire band towards the MEP. So a key improvement, for example, the climbing image method allows the highest energy image to climb uphill to the exact saddle point, ensuring the accurate transition state location. So how we can use these applications with AMS? So AMS, as I said earlier in our previous sessions, that it is a versatile software platform for computational chemistry and material science, which integrates various computational engines, including the fast and approximate density functional based tight binding method. Obviously, you can see this. This is actually the representation. And then the combination of NEB with the AMS DFTB is powerful because it allows users to study the complex large-scale systems that would be too computationally demanding for more accurate but slower methods like full density functional theory. So which includes the key applications like how we can utilize this in material science. So investigating atom diffusion in solid state materials such as ionic movements in batteries or analyzing phase transitions. Catalysis, that identifying the reaction pathways and transition states on catalytic surfaces, which often involves large surface models. Then obviously solid state chemistry for predicting activation energies of processes like defect formation and migration in crystal lattices. And then comes to polymers and larger molecules, studying the mechanisms of chemical reactions and degradation pathways in large systems where quantum accuracy is needed, but full DFT is unfeasible. So on a conclusion, let me say that in AMS, NEB calculations can be set up easily through the graphical user interface or with scripting, allowing for efficient exploration of potential energy surfaces. So this is actually the representation, as I said earlier. So what could be the output? It's a little bit, time consuming steps. So I will be taking care of all those steps, that how we can locate a transition state in a chemical reaction. And obviously the output or the exact, representation of this so-called transition state search can be found, and it will be something like this method. So this is the method that how it proves to locate the transition state in a chemical reaction. So likewise, the same application can be utilized in battery modeling. So we are discussing all those things in our coming lectures. So it will give you a clear-cut idea that how NEB can be useful in various applications related to chemistry, materials, and other solid state chemistry, and also in polymer and large molecules. Thank you.